Taylor's polynomial expansion allows you to represent functions as polynomials. This has lots of useful applications. For example, you can use it to compute functions such as the exponential, cosine, and sine functions to arbitrary precision. It can also be used to prove some important mathematical theorems, such as Euler's formula. Now, there are already plenty of resources out there which explain Taylor's polynomial. However, all of the ones I've seen take a rather unusual approach, where they assume that the function must be equal to some polynomial, and then work backwards to figure out what the coefficients are. In this video, I want to show you a better way of deriving Taylor's polynomial, one which is much more straightforward and simple. In fact, once you understand the basics of calculus, you can derive Taylor's polynomial with just one step. The only thing you need to know is the fundamental theorem of calculus, or FTC for short, which states that any differentiable function f of x can be expressed as the integral from c up to x of the derivative of f with respect to x1 plus f of c. The x1 here is a different variable to x, used as a dummy variable for the integration, and usually it would be called z or t or something like that, but I've chosen to call it x1 for reasons which will become apparent shortly. For those of you who've never seen the FTC before, you can derive it by simply evaluating this integral. In order to evaluate this integral, we need to find the antiderivative of the derivative of f, which is just f by definition. So this integral is equal to f evaluated at x minus f evaluated at c. And then I've just brought the minus f of c over to the other side of the equation. And importantly, this equation is true for any differentiable function f and any value of c. Now that we understand the FTC, we have everything that we need to derive Taylor's polynomial. So, suppose that we have some infinitely differentiable function f. By infinitely differentiable, I just mean that you can keep taking derivatives of f as many times as you like, and you'll always get back another differentiable function. In particular, f itself is differentiable, and so we know by the FTC that f of x is equal to the integral from c up to x of the derivative of f at x1 dx1 plus f of c. Now, since f is infinitely differentiable, then the derivative of f is also a differentiable function. But that means we can apply the FTC to it. So f of x is equal to the integral from c up to x of the integral from c up to x1 of the second derivative of f at x2 dx2 plus the derivative of f at c dx1 plus f of c. To be clear, I've just expanded this f prime of x1 term into all of this by applying the FTC in exactly the same way that I expanded f of x in the first step. And since integration is a linear operator, we can split this up into the integral from c up to x of the integral from c up to x1 of the second derivative of f at x2 dx2 dx1 plus the integral from c up to x of the derivative of f at c dx1. But we're not done yet, because remember, f is infinitely differentiable. So the second derivative of f is also a differentiable function. But that means we can apply the FTC to it. So f of x is in fact equal to this. But of course we don't have to stop here. F is infinitely differentiable, so we can carry on like this for as many times as we care to. Each time we do, we introduce another layer of integration into this leftmost term, and we introduce another term in this sum. In general, after we've applied the FTC n times, we will get an equation that says f of x is equal to this nested integral plus this sum. And there we have it. This is Taylor's polynomial expansion. Okay, if you've seen Taylor's polynomial before, then maybe this doesn't look too familiar to you, But we can simplify this expression a bit further. First, let's focus on this term here in the summation. Since the term inside these integrals is constant with respect to the variables of integration, we can just pull it outside of the integrals. And what we're left with is the constant function 1 integrated I times. When we integrate 1 from c up to xi minus 1, we get xi minus 1 minus c. When we integrate that from c up to xi minus 2, we get xi minus 2 minus c squared divided by 2 minus c squared divided by 2. And that last term is just 0. Each time we integrate, we raise the power by 1 and then divide by the new power. So after integrating I times, you'll end up with x minus c to the power of I divided by I factorial. And this is how Taylor's polynomial is usually presented, although personally I find the integral form makes it more obvious what's going on. Anyway, if this is Taylor's polynomial, then what's this thing? I promised you a way to represent functions as polynomials, so why is there a weird nested integral term here? Well, it turns out that Taylor's polynomial expansion doesn't always work. To be clear, this equation is always true. Any infinitely differentiable function can be expressed as this nested integral plus this polynomial. It's just that in general this nested integral term is non-zero, in which case this decomposition isn't that useful, because while the polynomial part is nice and easy to work with, the nested integral is a complete nightmare to deal with, usually worse than whatever the original function was. But fortunately, for most of the functions that you see on a day-to-day basis, this nested integral term will be small, and in fact will tend to 0 as n approaches infinity. This means that you can often just ignore it and use the polynomial part as an approximation to f. The more terms you include in the polynomial, the better the approximation will be. But in order to safely use this approximation, we need to know when the error will go to 0 as n is increased. In the usual way of explaining Taylor's polynomial, this nested integral is never shown. It is simply explained that there is some error term which corrects the polynomial approximation. But by simply applying the FTC, we derive not only Taylor's polynomial, but also an explicit formula for the error term, and we can use this to understand when the error vanishes. It's a bit difficult to understand how this term behaves in general. Nested integrals aren't fun to analyze. But we can simplify the analysis by considering a few different cases for how the values of the nth derivative of f at x change as n is increased. To start with, let's consider the simplest case where the absolute value of the nth derivative of f at x is always less than some constant value b. The absolute value of an integral is less than the integral of absolute values, which are less than b, and b is constant with respect to the variables of integration, so we can pull it outside of the integrals. And as we saw before, when you integrate the constant function n times, you get x minus c to the power of n divided by n factorial. As n tends to infinity, this expression goes to 0. In fact, it goes to 0 very quickly because n factorial gets larger much faster than x to the power of n for any constant x. The other thing to notice is that how fast this error approaches 0 depends on how far away x is from c. The closer x is to c, the slower this numerator grows. This shows that your polynomial approximation will be most accurate in the neighborhood of c, so choose your point c wisely. What we've just shown is for any function whose derivatives don't increase in value, the error term goes to 0. An example of such a function is e to the x, whose derivatives are all e to the x. Note that while e to the x changes with x, for a fixed point x, as you move to higher and higher derivatives, the value of those derivatives don't change. This is the condition that means the error in the polynomial approximation will approach 0 as n approaches infinity, for all points x and for any choice of c. But even if the values of the nth derivative of f increase with n, the error can still go to 0 so long as the values don't increase too fast. In fact, so long as the absolute values of the nth derivative of f at x are less than b to the power of n for some constant b, then the error will still converge to 0 for all values of x and for any choice of c. As before, b to the power of n is constant with respect to the variables of integration, so we can just pull it outside. And as before, the factorial denominator dominates the exponential numerator. If the absolute value of the nth derivative of f at x is less than n factorial times b to the power of n, then something interesting happens. The absolute value of the error will be less than b times x minus c to the power of n. And this can still converge to 0, but only when the absolute value of b times x minus c is less than 1. In this case, the error goes to 0 only for values of x which are within a radius 1 over b of c. Here's an example with the logarithmic function and Taylor polynomial centered at c equals 1. The derivatives of log x grow factorially fast, so we don't get global convergence. Instead, as we add more terms to the polynomial, it becomes a better approximation, but only within the interval 0 to 2. Outside of that, it veers off wildly. In summary, as long as the values of the nth derivative of f at x don't grow too fast, the error term tends to 0. And most functions you see on a day-to-day basis don't have rapidly growing derivatives. And finally, there's one more reason why I like this FTC derivation of Taylor's polynomial better than the standard way. And that is, it makes it really obvious that you can use different values of c. I mean, think about it. The fundamental theorem of calculus works for any value of c. So clearly, we can choose to use different values each time we apply the fundamental theorem of calculus. And when we do that, we end up with this expression. Instead of being centered at a single point c, each term in this polynomial comes from a different point ci. Why is this useful? Well, oftentimes you don't want to approximate a function only for a single point. You want to approximate a function on an interval. In this case, you might be able to get a better approximation by spreading the ci points across the interval. For example, suppose that we wanted to approximate the exponential function on the interval -3 to 3. Usually, you would just use the Taylor polynomial centered at the midpoint of this interval, 0. And as long as you include enough terms in the polynomial, this will work fine. But we don't want to bother computing hundreds of polynomial terms. As you can see, if we only include 6 terms, then our approximation becomes quite bad for values less than -2. If we instead spread the ci points out a bit when constructing our polynomial, we get a much better approximation for the interval that we care about, while still using the same number of polynomial terms. To conclude, we managed to derive Taylor's polynomial and an explicit expression for the error of the polynomial approximation, and a generalized version of Taylor's polynomial simply by applying calculus over and over again. So the next time you forget how to do Taylor's polynomial expansion, remember, it's just calculus.